Alright guys, so we are going to go through some graphing examples that I think will really help you out on the things that were missed on the quiz. So the first one we're going to look at is this first example. A car starts at a red light, speeds up, gets to a constant velocity, then slows down to a stop, and then reverses speeding up and slows to a stop. So this could be an example like a car speeding up at a red light, then going at a constant speed, seeing a red light, slamming on its brakes, but accidentally going in the intersection, so it's got to go in reverse, and then stops when it's back before the red light. So pause the video and write that down. Alright, so I'm going to put this over here. So we're going to talk about graphing this. So we want to be able to graph it position time, velocity time, acceleration time. So I'm going to draw my position time axes. These might not be big enough, but that's okay. So starting at a red light, we don't know what the starting position is, so I'm just going to say it's 0. Okay? Moving forward, speeding up. So that would be something like this. Going at a constant velocity like this. Okay? Slowing down to a stop would look like this. Reverse is speeding up, then I got to go back the other way. And then slowing to a stop would look like this. Okay, so we have this part where it is speeding up, constant speed, slowing down, speeding up in the opposite direction, and then slowing down again. All right, let's look at the velocity versus time. So speeding up in the positive direction looks like this, constant speed, slowing down, then moving in the negative direction, and then slowing down again. Okay, acceleration time, something like this. We look at this slope. So the slope on the velocity graph is positive, then it's 0, then it's negative for a while, and then it's positive again. So this part and this part are showing this negative line right here. All right, let's try another example. All right, our next example is throwing a ball at a wall and the ball bounces off and goes back the other way. We're going to graph this, and then I'm going to ask you to, we're going to add some numbers, and we're going to find displacement and acceleration. So why don't you go ahead and try that on your own. I'm going to draw my axes. And I'm actually going to change this to the Y. Let's talk about what it looks like in the Y direction, okay? So you throw a ball. When you throw a ball, you're going to start from somewhere not 0, right? Because you're not throwing it from the ground. You're throwing it from your hand. You're throwing it at a wall, so you're throwing it with a fast velocity. It's going to immediately start to slow down. So something like this for the throwing of the ball. Now the ball hits a wall. It's going to reverse direction, right? Except in the Y direction, it's going to keep going. So maybe it'll keep going like this, and then it'll turn around and come back and hit the ground. So if this is our point where it hit the wall, because the wall reverses the X direction, not the Y direction. So let's try the X graph as well. Position versus time. So if the ball is moving at a constant velocity in the X direction, right? And then it hits a wall. Oops, sorry, that should not be there. Let me undo that. How do you undo? Whoa. Okay. We're just going to draw this in a different color. Okay. Ignore that. It's moving at a constant velocity, right? Like that. And when it hits the wall, it's going to bounce back in the other direction, so in the negative direction. So for our velocity time in the Y direction, it's going to be slowing down the positive direction and then speeding up in the negative, and then we're going to have a constant negative acceleration because the ball's in free fall, right? Ignoring the fact that this bounce won't be perfectly elastic, which is assuming that it is. Now my velocity versus time graph here, okay, I'm going to have a positive velocity, and then it's going to hit the wall and have a negative velocity. We know that the acceleration is going to be 0 the whole time because for projectiles, they're not accelerating in the X or Y direction. All right, let's add some numbers on our velocity time graph in the Y direction. So let's say this is a starting velocity. You can throw it at 10 meters per second. And let's say it reaches its apex, so the top of its path, at 5 seconds. And it hits the ground then at 12 seconds. Now I didn't make that, no, that's not going to make any sense. Yeah, it is. Okay. I didn't make it at 10 seconds because it's going to have to go further down here, so I needed to add some time on there. So 12 seconds. I want you to, from this graph right here, this one right here, calculate its displacement over the first 12 seconds, and also tell me the acceleration. So pause the video and do that. All right, so for the displacement, we take this triangle plus this triangle, right? So we're going to do 1/2 5 seconds times 10 meters per second. So that's going to be 25 meters, right? And over here, we're going to do 1/2 7 seconds times, we don't know the final velocity, let's just say it's going negative 13 meters per second down here, negative 13. Okay, so hopefully you got negative 45.5 meters. Add those two up, 25 plus negative 45 is negative 20.5 meters for the displacement. So that would be delta x. Now the distance, what would the total distance be? $70.5 meters. Okay, because you would take the negative away. Now finding the acceleration, you want to look at the slope. So we made it free fall, so it should be negative 9.8, but we can check that. So to find the slope, let's say the acceleration at 2 seconds right here. You would look at the slope of this entire line because the slope is constant this entire time. So I would just do the change in velocity over the time. So that would be negative 10 meters per second, right? Because it goes from 10 to 0 over 5 seconds. So you should get an acceleration of negative 2 meters per second squared. Now that doesn't make sense in terms of I said it was in free fall because I just made those numbers up. But that's how you find the acceleration at this point right here. You find the slope of the entire line. Okay? All right, you're going to answer some questions and then you are done.